we have studied waves in considerable detail, and we have found that they seem to describe the behavior of light. But in the last film, I showed you an experiment in which light seemed to behave like a particle. We now have two ideas about light, waves and particles. Which is right? Well, in some sense, both ideas are right, and to show you this, I will do an experiment in which the wave properties of light and the particle properties are seen at the same time. Here's our apparatus. It consists of a light source with a slit in front of it. The light comes along here and goes through a hole in this baffle, which is designed to keep out stray light. And then the light strikes this double slit here, which can be moved back and forth by means of this electric motor and this mechanism. And I have this pointer here to keep track of its position. When the pointer moves in this direction, the slit is coming towards me, and when I reverse the motor, the pointer reverses and the slit moves away. Let me stop it here. Then the light goes along, and if I turn on the light switch, I can look down in here. We can see the interference pattern we're all familiar with. Bright bands where the waves reinforce, alternating with dark bands where they cancel. This is a typical wave phenomenon. From the geometry of this arrangement, we can calculate the wavelength. You've done it yourself in the lab. If I move this double slit, the interference pattern moves. Now, if I put this slit in here, like this, then when the interference pattern moves back and forth, more or less light will get through that slit into our photomultiplier, which I can put here. This is the same photomultiplier that we had in the last film. Here's what happened. Here's our light source with the slit in front of it. And here's the box. And here's the photomultiplier with its slit. And now I can draw the movable double slit on this plate of glass, somewhere in the middle, like this. And then light comes along like this and goes through the double slit and forms the interference pattern down here, so that there are dark bands alternating with light bands, something like this. Now, when I drive the double slit back and forth, I sweep the interference pattern across the photomultiplier slit. Now, for instance, light is getting through that slit into the multiplier. Now there's no light. Now there's light, no light. So that we expect that the output of the photomultiplier would consist of maxima and minima when we drive the double slit back and forth. Of course, we could have moved the photomultiplier or the light source, but it was more convenient to move the double slit back and forth. Now let's see it happen. I'll connect the output of the photomultiplier to this meter. And then when I run the double slit back and forth, the reading goes up. Here's the maximum. Now it's going back down to almost to zero, and there's the minimum. And let me leave it on a maximum. Now, if we're to see the effect of photons, we have to use dim light, as before. And the first thing I must do is to cover this apparatus to keep out stray light. I'll dim the light source, and I must use more and more sensitive ranges of this meter. And now the current coming out of the photomultiplier is about 10 to the minus 9th amperes. Let's remember that number. We can put the output of the photomultiplier on the cathode ray oscilloscope. And you see, we have the same kind of pulses that we had in the last film. Besides looking at them, we can listen to them. I can use this amplifier and this loudspeaker. If I turn the light off, all you hear is an occasional background tick. Now let me move the double slit back and forth, and you can keep track of its position by looking at that pointer. Now you remember that we left the slit at a maximum of the interference pattern. In fact, it was the central maximum of the interference pattern that you saw a moment ago. Now I'll start the motor, and you notice there are fewer pulses. The sound is coming down. Here's a minimum. Now it's coming up again. This is the first maximum, a minimum, and the second maximum is lost in the background. Now I'll reverse the motor. We'll go back through the pattern. Here's the minimum, and here we're coming into the first maximum. Another minimum, and here's our central maximum. We're going on past. The pointer is in the middle. Here's the first maximum on the other side. Minimum, and again the second maximum is hardly distinguishable. We have an interference pattern. We could have plotted it just by listening to the sound. Now let me bring it back to the central maximum. And look at those pulses. Listen to them. They are caused by photons. We saw that in the last film when we found no delay between the emission of electrons and the turning on of the light. Photons, particles, are forming an interference pattern, a characteristic wave phenomenon. Now look at this. You remember that the output of the photomultiplier was about 10 to the minus 9th amperes, and that it had an amplification of about 1,000,000, so that the current coming in here must have been about 10 to the minus 15th amps. That's 10,000 electrons per second. Not every photon that strikes the photomultiplier produces an electron. Some get lost. On the average, only 1 out of every 1,000 photons succeeds in producing an electron. That is 10 to the 3 photons per electron. So that if we have a current of 10,000 electrons per second, there must have been 10 to the 7th photons per second entering the photomultiplier. That means that on the average, there is 1 photon coming in every 10 to the minus 7th seconds. These photons travel at the speed of light because they are light. So that by the time a photon has reached the double slit, the one that preceded it has been absorbed in the photomultiplier. In fact, if the photomultiplier weren't there, that photon would be 100 feet away, as you can easily figure from the speed of light and the time between photons. This means that there is rarely more than 1 photon in here at a time. Let me go over that. A photon comes along here, all by itself, goes through the double slit, continues along here, still by itself, and ends up in a bright part of the interference pattern, never at a minimum. Now, this may seem strange to you, but it's the way light behaves. What can we say about it? Well, here's some waves, and you can see them. And here's a particle. It's tangible. But can you see the waviness of light? Can you handle a single photon? No. We observe the behavior of light and compare it with models. This model for waves and this model for photons. But neither model is capable of describing the behavior of light accurately by itself. Baseballs don't show wave properties. Water waves don't act like particles. Nothing that we've discussed acts like particles and waves at the same time. But light can and does. All the experiments that have been performed show it. How do we interpret these results? Well, where there's a maximum of intensity in the interference pattern on a wave theory, we are most likely to find photons. Where there's a minimum, we find none. With this description of light, we are able to predict its behavior, and for the moment, that means we understand it.